All right, welcome back. And let me first maybe introduce myself. I'll be moderating a lot of the talks that coming up today. My name is Abdo Hassan. I'm a poet, AI strategist, critical theorist, and I work often in the intersection between critical theory and creative computing. So a lot of these talks to me hit a very, very intimate note because they cover the theme of wildness, of being wild. And maybe I want to ask everyone in the audience now to meditate for just a quick second on the word wild. What kind of imagery does it bring up? What kind of associations do we have with it? And what does it really mean to be wild? And actually, I would like to borrow or use the help of a quote from Jack Halberstam, the author of Wild Things, where they say, "I want to think with you about wildness on the one hand and move towards an aesthetic of bewilderment on the other." Bewilderment is a really interesting word in English. It means, in a way, becoming wild. But more than that, it references becoming lost in time and space. Bewilderment is a kind of permanent orientation to unknowing, unthinking, and unbecoming. And let this kind of set the tone a little bit to what we're about to discuss in this 10th edition of the Fiber Festival, where in the context program, we're going to provide space for knowledge exchange, contemporary developments in art, sound, and media to explore this particular theme. Through keynotes, panels, artist talks, today's program questions, what can we learn from the existing landscapes, both ecological, technological, within which we exist? How do we artists translate wildness into sound, imagery, and movement? Can digital and algorithmic environments foster more than human relations, or do they replicate extractive monocultural systems? But of course, we have to say this with a little disclaimer, right? Because the word wildness or something, deeming something as wild, has often not been an innocent term and has been used as an extractive kind of logic for, let's say, Western colonial imagination, used to frame people, landscapes, and ways of being as something to be conquered, disciplined, and erased. So we want to do two things. We want to explore wildness and see what we can learn from it, while still being critical of the overhead that it still carries. So to do this, we have our first artist talk, right? Block of artist talks, with a thematic focus on wild processes and fluid technologies. So we are going to feature two artists who channel unpredictable natural phenomena into their arts. We explore how embracing material wildness, whether in sound or in computing, can lead to new aesthetics and ecological insights. So we have both Navid Navab, and we have Ioana Vreme Moser, who are going to be looking at both alchemic sound and fluidic computing as a tactile, eco-inspired alternative to silicon electronics. So I would like to welcome first, one second, Ioana, who is a transmedia narrator and sound artist. Her talk will focus on the fluidics as a future alternative to electronics and reveal a parallel history which technology tunes into natural cycles rather than overrides them. So with a warm welcome, I invite Ioana on stage.
Thank you. Thank you so much for having me. I've been spending my last year researching a lot of very in-depth course of electronic processes, and at some point I stumbled upon this image, and I saw these very bizarre shapes that you find there on the right. Just to state, this isn't from an engineering book. And I was quite intrigued. I was like, what is this? What are these shapes? And it seems that they are actually computing elements. So on the left, you will see a CMOS chip, so inside of a modern semiconductor, a mineral semiconductor. And on the right, you will see a fluidic chip with a logic gate. Both do the same thing, but they look very different. It's as if one defies the other in form and shape. So I was intrigued, and I tried to find online sources about what is this technology, when was it developed, and I could find nothing. So I went deeper down into archives, and I discovered that almost at the same time that the transistor was invented at the Bell Labs, there was another type of transistor called the fluidistor, invented at Diamond Labs. And I wondered why nobody knows about this, why there's no discussion about it. Well, it seems that this whole technology failed. It failed because it was too slow. So I took this transistor and I remade it, a process which I called de-archiving, which means that I take something from an old pattern and I put it back into function. And I wanted to see if this had already a history. And it seems that computing was always linked to water. They were the first computers that appeared very simply as water balls with a hole, and they would sing to show units of time. There were astrolabs, and there were other computers that would show the movements of the sky, like this Chinese Susong's astrolab clock. Then there's Al-Jazari. He's also making astrolab clocks, but he's also making perpetual oscillators. So this is called a perpetual flute. It's provoking constant movement. And I was intrigued, okay, there's all this parallel history of technology that uses natural materials like water. But we actually don't know so much about it. This is a little bit later where a number can be calculated by dipping something into water. Analog computing. And then there is the case of the Moniac, which I find to be one of the most interesting because the Moniac is an analog computer that functions with water. It shows numbers in quantities of water. And it's invented by Bill Phillips. And this is in the 1930s. He says, well, money flows and so does water. So he sets to build a model of the Great Britain's national economy with water. And this computer becomes one of the first computers that will model complex systems. So just so you can see how it works, I will play a little video.
That powers these two parts over here, which is where money can actually come into the economy. The actual water flowing around is the money going through the economy.
That enabled you to illustrate, for instance, what would happen if you try to grow the economy, pump more money into the economy. For instance, you could increase government expenditure and see what the effect of that is through the workings of the economy, the interaction of all the variables on growth. Of course, if the economy is very prone to imports, people might simply spend their money to import foreign goods. Or if the economy is operating at a high level of activity, then that would lead to inflation.
Indeed, inflation it is today. But another very intriguing technology that comes just after is fluidics. And actually, the rest of the talk will focus about this. Here you can see different fluidic computing elements, from very small to very big. Size doesn't actually matter that much. It just gives a higher speed and a higher frequency. So what are these shapes, and why do they look like this? Because form follows function. Each shape is very designed to guide streams through its inside. So they were making them out of different materials, carved as cavities. Here you can see a Soviet system where these chips are milled inside the material and then produced to be very resistant. The main advantage to these systems is because it works with fluids, air, and water. You can send them into space, they are resistant to radiation, and they are theoretically indestructible. Something that modern technology doesn't really stand for, right? Modern technology, electronics especially, are very sensitive. So, what did they use them for? Well, there was aviation, there was space exploration. This circuit was supposed to be sent into NASA. It's designed by NASA. It was supposed to be sent into space. And then there's automation. All the robo-arms in the factories, they used the system. There's also an idea from Tadeusz Gierkiewicz to create an alternative communication network. It's a very funny, this is his PhD paper. And then there is computing, the part that I was the most interested, because there was a computer called Fluidic, which operated as a full Turing machine using fluidics. Why did it fail? Well, it was too slow for the market. It didn't catch up, and like a lot of different inventions that were in the 20th century, it got lost in obscurity. So how does it work? Let's look at this video, which shows you how these shapes work, using the Coanda effect, named after Romanian physicist Henry Coanda.
При приближении стенки струя примыкает к ней. Это явление получило название эффекта Коанда. С ним мы часто встречаемся в повседневной жизни. Рассмотрим, почему он происходит. Эжекционные расходы с обеих сторон струи равны. При приближении стенки сечение снизу уменьшается, скорость эжекционного расхода растет, а давление падает. Поперечный перепад давления прижимает струю к стенке. Эффект Коанда связан с подсасывающим действием струи. Эффект работает и на затопленной струе. На положение струи не влияет появление дополнительной стенки. Оторвать струю от стенки может сигнал управления. Если его снять, струя не возвращается к первой стенке. Таким образом, реализуется свойство памяти.
So what he says there is very interesting, that basically these shapes can deflect streams. You have a very narrow stream. You can move it in the shapes, and you're able to memorize the position of the jet by using these control ports. So I was very intrigued by this, and I made the first piece where I took this shape, the fluidic transistor, the fluidistor, or the memory unit, so it's a flip-flop, and I made it from glass, and I connected 3 of them to create a shift register, more or less, so a next unit of memory. So then the water starts to move inside this machine, and each time it memorizes 1 bit of information, there is this very subtle sound. So I added salt in the water so that I could intercept when there was water and when there was no water. So in a sense, it's a digital system that works with yes or no. And then I was more intrigued about these shapes, because, for instance, if you take a fluidic transistor and you take the arms, you look at it, it's like a little human. You take the arms and you feed back the arms back into the legs, you obtain an oscillator, right? So an oscillator is something that creates a perpetual motion, and a fluidic oscillator will move the fluid from left to right, creating a turbulence, a constant turbulence. So when we look at it in sound, and if we put air inside this form, what we obtain is a whistle. Up. So that's a very subtle oscillator. The air is moving inside the shape to create the tone. And if there is water, and if we enlarge this feedback path, we get a certain kind of vibration. So here you can look, the water is going from one leg of this little humanoid to the other, creating a movement, a vibration. And there's also a closer shot. So when the pressure needs to build up to a specific amount, and then it starts to dance, in a sense. So I found all these movements very fascinating, and I also wanted to index all of these shapes, and this is when I got into the logic and into this alphabet of these parts, because they look very intriguing. Here we have in the left, for instance, this is an X-ray of a computing unit. Some of these shapes are designed after the human throat. For instance, this is a logic element designed after an anatomical feature. There's AND gates, there's OR and NOR gates, there's adders. You can combine them to make circuits, and at the end, these are all shapes that I have rescued. I also have them here in cards and indexed, and I want to see what combinations I can make with them. Therefore, I created this fluidic workshop where these shapes are made of panels, and you can combine them like a little modular system to create different circuits. And then I was also very intrigued to see how much I can expand this system and how I can make more complex things, because we are at the level of very abstract little components of a computer. So like the Moniac was modeling a natural, I mean, it's not a natural system, it was modeling an economy. In my case, I was interested to model the architecture of a modern computer, but to model it with these shapes. So I took elements such as comparators, I built an analog computer, such as pulse shapers, and then the processing unit becomes this massive system which is entangled in tubes and forms, and each of these shapes passes bits of information as quantities of water, or some as quantities of air. And when I designed the sound part, because the sounds that you hear, they're all very pneumatic, it's just the pumps, and then there's the pressurized air, compressed air, which passes through the shapes and then makes this whistling. So they're oscillators made from these particular shapes. And to patch this system, of course, it's to program it in a way. I have to connect it with tubes. So I spend days and days just connecting different elements to each other, making a diagram of the function that I want to achieve. And the question is always, is it really working? Well, it's kind of complicated. It is working to a certain degree, and it is not working to another degree, because there is gravity and so on. But the shapes themselves work, and when you put pressurized air in them, you are gonna hear the sounds. So this is also, it's creating more motion than actual computation. It's an idea. So the final piece becomes this massive fluidic computer that you can walk inside and see what kind of shapes, how basically computing elements look like when they are not designed with electronics, but rather when they run on water and air. Thank you very much.
Thank you so much. I actually, let me first maybe take a moment to address the audience, because there is a story we're often told about computing, about like the history of the transistor, the electronic transistor, and how it has become this hallmark, this defining logic of why computers are the way they are now, right? Without ever exploring these alternate histories of other forms of transistors as a way of like introducing new variables to the equation of computing. I want to ask you maybe about the future questions that you're going to explore in your research. How are you going to develop this? You also mentioned slowness as a side effect of these ecosystems. So what is next, basically?
Yes, I'm working on a fluidic cookbook, so I want to release all this information and all these shapes that you see here as well. I want to print them in a book and to give them, like, basically make them accessible as also as a toolkit.
Yeah. These are the same shapes we saw in the presentation.
So these are all archival shapes. They are not made by me. They were found in these books, like this kind of books. And basically it's kind of a revival of this whole technology, which, because it was such a speed date, I didn't have time to really get deep into it. But, you know, it was developed from the 50s all the way to the 80s in all across the world, especially in the eastern part of Europe. So I was really interested in finding these people that develop it and why it failed and where it failed.
Yeah.
And I want this to be published into a book.
There is so much I want to ask you, but I think it's also a good moment to also lend to the wisdom of the crowd. So maybe there's a pressing question that someone has. A provocation, a question. We have a question here. Yeah.
I didn't use current computer technology. I think it's very as an analogy to understand.
What can we learn from this
No,
practice?
I think it's actually a really great educational tool, because you can really see how these forms function, and you can understand logic functions by looking at the stream, because you're switching. And again, I didn't have time to show how this works, but you basically collide two streams and then you bring them into another outlet, and that's a logic condition, you know. And I feel like when I explain to people and I show them, people are like, oh, this is how a logic gate works, you know. So it's really great as an educational tool. If it's as performative as electronics, no, it can't be, because it's limited to the speed of the airflow. So you have resistance and things like this. But I find it actually quite poetic, you know, that it's limited to a certain,
And this is where like slowness comes in.
That's where the slowness comes in, yeah.
But is it, I had a maybe a slightly technical question, because transistors are quite deterministic, right? Like the current goes through them and you get the same result always, depending on kind of what's going through it. In this case, are we replicating the same determinism, or is there kind of emergent random behavior sometimes?
I mean, there is a lot of random behavior because of things like especially in the works that I made, because of gravity, because of the bubbles, because, you know, that things kind of happen as they want.
Like
I can't really control. Theoretically, you can make it very controlled, but also to say a lot of these elements, they're also analog as well as digital at the same time, a little bit like the transistors, you know. So, and also here you can see this is how they originally looked like. They were not visible. The shapes were hidden. It's like it's like a chip. It's like a computer chip, but it's inside. So the shapes were never seen. This is also why I got so intrigued by the forms themselves, that they're so beautiful. And
Wow. I don't know if you have maybe one last pressing question. Maybe at the end of the room. I saw that one first. I'm sorry.
Thank you. How did you determine the type of water you wanted to use, the temperature of it, also of the air around there, because it's oxygen, but obviously there's different types of air, I guess, and different chemicals in it. And have you explored just different types of water, consistency, different type of liquids, different types of air, what effect would it have, things like that? different planets. I don't know. Just just take it as far as you can.
Well, the problem here is
Great.
that I don't have that much money, so I actually did this all quite DIY, and I was using distilled water because I was afraid to get this bacteria growing inside, which is always a problem when you do waterworks, you know. And for air, I just like to use the simple air of the room, so it's just the room itself filling the space, because this is what I also like about this technology, that it just works with what is there somehow. I mean, the water, of course, it's something special, because you have to have you could theoretically also make it with muddy water, but then if you have a little bit of grains and particles, they get stuck into these tiny nozzles, you know. So this is a future question, actually, what you can possibly use in these things. They do historically use concrete. They were using oscillator to mix concrete, so there were applications where the material is viscous. I personally haven't tried with viscous material because I just have so little of these pieces that I don't want them to get stuck with anything inside, so I take care of them. Yeah.
Well, beautiful. Thank you so much for walking us through this. This is wildly inspiring and a really great start to set the tone of the whole conversation. So maybe another round of applause for Ioana. And we're actually going to stay on theme here, right? Because we talked about kind of this alternative or kind of new way of thinking about transistors and computing. And we're going to really stay on topic with another wonderful speaker who's an anti-disciplinary composer. I love the term. With a background of contemporary music by medical sonification and philosophical biology. So I'm talking about artist-scientist Navid Navab, who in his artist talk will invite us into his world of alchemical media art installation, which balance between musical instruments and scientific installations. Really excited to welcome Navid on stage. Are we? Yes. There it is. A big round of applause.
Press play. Check. You hear me well? Okay. Well, talking about staying on theme, I've been lucky enough to be paired with Ioana in a few festivals this year, and through this conjunction, totally one of my favorite artists, and I think we're thinking about similar things in different realms. So happy to be together in the same program again. So this talk is going to be a little bit messy, and I'm going to talk fast at first so I could give you a quick overview of how I got to where I am with the current project, which is being the concert version of which is being presented tomorrow at Orchel Park at 7 p.m. at Fiverr. Okay, so I come from, currently you've heard the word art science. We're looking at how we converse with nature. There's a zone within which you can't really apply scientific methodology to. You need to also think deeper and engage and bring the senses in. But I associate even stronger with the alchemical tradition, because then there's also there's a hidden meaning. So as alchemists were looking for gold, they were also looking for something else. Here you could see the ladies holding an Ouroboros snake, and there's a devil-like feature above. So the Ouroboros, you could come to realize it not just as a chemical scientific thing, but it's the recursivity of life itself, matters of process that we are part of, forces of nature that inform us as we find ourselves within them. So if we find how to live with these forces, or the quest for finding how to live with these forces is the real gold. And that's where all my works are trying to do. I'm trying to find how to exist with forces around us in this ecological, political moment. So I'm going to take a slice through my journey. There's many different slices to be taken. Since the concert tomorrow is music, I'll take a musical slice this time. So through that way of going through what I do, I started with improvisation and music. So what you see on the top left is the guitar string, and then right next to it is the textures of a nail. And when I was performing in that world with materials, things could shift. The phenomenology of performance could shift really quickly. So the guitar string could become a score, the nail could become the interpreter, and then going to technology, that was lost. So I was constantly working with technology to bring my body back into the performance when performing with musicians that were in the spot, whereas electronics don't let you do that. Some of these videos might be for grant applications, might have too much text over it. Don't worry about it. So this is all improvised. I had to create instruments to be in the moment with other musicians who were being in the moment. But that wasn't quite enough, even though these kind of interfaces helped. The way the whole phenomenology of performance would flip with materiality and the existence in the moment, I wanted to find a way to go back to that. So I started thinking, okay, how do we go back to a post-schizophonic world? Schizophonic meaning schizo-separation of phono from voice. So I am here, my sound is over there, somewhere in a speaker, and your brain has to put it together. There's a disconnect somewhere. So I've been trying to bring that all together. So I started creating instruments that allow me to do that. But it's different than turning the world into a mouse click. I was trying to work with texture of materiality at the level of milliseconds. Meaning it's not like the eggplant's not a trigger, but how you touch it, how you scratch it at a level 10 milliseconds would shape the performance. That would allow me to create scenographies that then the performers would perform within these kind of sonic environments while the musical event would emerge through improvisation. You could go on my website for more, but then through a twisted event, twist of fate, and meeting different people at different conferences, I ended up in the medical field, where now there's patents, publications, so it's not speculative or academic. It's actually in the real world. The research has been doing that for 10 years or so, but I did start going in hospitals, university campuses, Zurich, Balgrist University Hospital, trying to see what the problems are. And the problems were similar across the field of music and medicine. So this kind of embodiment, connection with materiality, or who decides what is signal, what is noise. And top surgeons, like top violinists, that don't like to move to interfaces that make things far too musical. Surgeons also don't enjoy when a technology says, this is right, that's wrong, because sometimes you're listening through your body. So I went farther. I tried to, in the field of medicine, create more technologies that get me closer to fibers of materiality while sonifying them. There were some results. Then I'm going really fast, but I want to get to my current work. Then I created another installation based on these discoveries to work with thermodynamics of temporality or temporal textures of materiality where things are not so linear. So for example, what is the rhythm of water boiling? And so I was trying to imagine the history of sound recording initiated by Edison horn that used to etch voices in a wax cylinder where schizophrenia was first created, let's say, referencing this history to project a different liquid future where your voice would go through three alchemical chambers for alchemical sonic purification. One breaking down your voice from words to phonemes to silence, the other one's boiling it to extract phonetic vapor, spectral mist, and all the sonic content would be what you gave the installation that's stitching it back together through temporality of matter. I'll give you a very quick sample, but then you could go on my website and see more if you like.
Sont les fantômes.
So then I wanted to go farther into fibers of materiality. And that made me realize I need to completely let go of self-expression, digital forms and grids, and really work with formation, where the emergence of self and the world or forms are at play. So instead of composing forms through self-expression, you have to inform dynamics of formation. So you have to work with forces around you that are alive, which brings us to the theme of wildness. So how do you work with things that feel alive? And I have that knowledge through working with musicians and dancers, so then how do you bring that knowledge to materiality? So that's the work that's being presented, called Organism, which has an installation and a performance version. Now, I didn't wake up one day deciding to create a work like that and ship it around, which I've worked really hard to make it ecologically sustainable and lightweight by moving it around slowly around Europe. But that was never the plan to create a work. It happened to me in a way. So this is the second oldest church in Montreal, and they approached me to sonify weather patterns through it. And then the plan changed. It went through gentrification. And then I went into the belly of the organ, and I saw pipes that were being disrespected, smashed, and this is a really amazing organ. So I took the pipes that allowed me, and I started exploring. And right around here in my early explorations, the pipes weren't meeting their energetic requirement, but one of them did. But then it didn't sound like an organ pipe. So I was quite baffled. I was like, what am I listening to? What is that? So I realized pushes and pulls of air were creating timbral interdependencies. And I thought about it for several months. And I was like, is there something there? Is there not there? And I realized turbulence and turbulent patterning was somewhere in there. So I started exploring. The same way musicians started like creating prepared piano. If you think musically, I started thinking prepared organ by going back to its materiality. I took the first prototype. So the piece had a public engagement sort of methodology, meaning that I put myself up for failure in front of publics many times because it's a very complicated topic and instrument to communicate concepts of. So it's a work without a premiere that I had like 5, 6 versions, and each one had a little soft public showcase, and I would see what would happen and would take that back to the work. So the first version, I had this review at Festival Music Actual, the Victoriaville, which at the time was not great, but then I started looking at it and I was like, so the person who was writing the review didn't realize I was playing the organ and there was no digital samples. So that was already interesting, which then I realized as an artist it's my job to communicate that to the public somehow through scenography and communications of sorts. But then this sentence, a cannon that blows smoke, suddenly made me realize, okay, cannon is the military, smoke is the wildness of nature. So we have the military cybernetic complex right here. And organs are supposed to represent our conquering of nature, to represent this highlight of civilization, of dampening nature's wildness so we could control ourselves through this conquered nature, to represent idealized versions of nature, such as harmony and pitch and 12-tone ideology, to be precise. So this control over nature is the site where nature becomes cultural. So instead of taking a nature that has already become cultural as an instrument and playing with it, I decided to open this up and be like, I want to play with the becoming cultural of nature within the performance itself and develop a culture out of that and let that emerge. So I started exploring and with turbulence. And these were very early experiments. So I was hearing things that didn't quite make sense in terms of what I thought was in the system. Emergence of timbres that were delicate, microsonic, and not organ-like. So I started going into the physics of organ pipes. And this was really, from an art science perspective, dramatic, the literature in there. There was a paper called Controversies at the Edge Tone of Chaos. I was like, is this an opera or is this science? Because what was happening is that at some point the laminar flow, okay, what you're looking at is if this is a flute pipe, like an organ pipe, at the bottom there's a little box where air is pushed through an edge. And let me see, like, if I can. So that's laminar flow pushed through the edge. Laminar flow is like prepared air, same way clay makers prepare their clay. It's prepared to take shape. And then it curls around and becomes turbulent flow. But at some point, the turbulent flow locks into dynamic unity with the laminar flow. And the controversies are when, how. And then we've seen through philosophical biology regarding how life emerges, consciousness emerges. When there's discontinuous shifts, the linear ontology can't be used. Liveliness emerges through these processes. So I went farther into, I'm going to go like about 1 minute over time to at least take some of the points home. So I went farther and I discovered this phenomenon called edge tone jumping. So at the physics of, and I want to take you basically what I mean when I say this work is about working with turbulence of nature. So it's not a concept, it's actually a methodology for working with it musically. So vortices are shed at the edge. Vortex shedding is what happens when you have Aeolian harps of all of these vortices are born and then they have a musical inharmonic. But when you overblow a pipe, suddenly it jumps by an octave or a seventh or an unpredictable amount. And this happens spontaneously, a word that linear physics or linear thinking doesn't like. And then the vortices give birth to a colony of baby vortices within them, and that's how you get multiphonics. And then the resonator of the pipe is like a curator for the shed vortices. But organs are traditionally made to get rid of all this stuff and just give you a tone. But then here we have this alive site where things could become really unpredictable, jumping. And so I started creating methods for working with this aliveness of nature by bringing improvisation and comprovisation and finding the sites where things are unpredictable, maybe intentional, and then putting these into play. And that's the final instrument that you could hear tomorrow. Thank you. And there's a lot more I could share, but you could talk to me later.
Wow. Thank you so much. I mean, there's a ton of things I want to ask you, but I think it's more urgent for me than ever, and that's a key takeaway, is to go to your website. Because that's where all.
Yes.
So no, there's naturally a lot we can discuss, but I want to be a bit more generous and give the audience a chance to ask a question, because there's been a lot of great things shared, and I'm wondering if there's question, provocation, or else I'll go. I have no issues. Yeah, there's a question here. Okay. So yeah, this is a question just for people who couldn't hear. This is a question about the logistics of the organ itself, and how you are allowed to take it home.
Well, a billionaire bought the building, rented it to a millionaire. The millionaire wanted to work with culture, approached Media Labs, and they heard me and some of my colleagues are good at working with in situ sites. Then it got gentrified, and then I realized maybe that was a tax cut or something. I don't know. And then I documented how the organ was being disrespected, and I asked if I could take it, and they said, no, we're going to restore it. And I was like, why don't you get a quote? The quote was $1 million. Sorry, there's a lot of millions involved.
Yeah.
And then they were like, you could borrow it. And I took 3 trucks and borrowed it.
Wow. Wow, beautiful story. No, and I think maybe just as a closing note, I think that it's incredible how you're able to navigate from like the materiality of the objects and the wildness there to like the biological philosophy of working with liveliness. What are kind of because I see a tone, and we've talked about the ethical implications of working with such like wild systems and introducing wildness. So maybe if you have a final note on this kind of point.
Yes. So there's where ethics and techniques come together. So to work with sites that are alive, first of all, humans have a hard time already working with each other, but at least we have that knowledge of another force that's alive and what it feels like to respect something else that's alive, to work with it. So there's already an ethics there, and then we see that in music. So as a composer, if you tell an amazing musician to play your notes, you haven't really taken their life force, or you haven't preserved their life force, you have expressed yourself. So, and same with dancers. So if you work in the world of improvisation, you feel a body, you come together, forms of coming together, holding together, which means that at every instance, everything matters and everything has to be counted. So then you could take that knowledge to materiality, but not conceptually, through thermodynamics and energetics, seeing how liveliness emerges from reservoirs of indeterminacy of dimensions of time folding into each other through chaos and turbulence, and see how we could work with that instead of conquering it. So there is a kind of a collaboration and preservation of forms of life without adhering to the binary of alive versus not alive. We could work with, there's a degree of liveliness that emerges in nature, and life emerges from that.
Beautiful. I think this is going to be a great segue into, it's almost like you're advocating for a new type of like systematic world building like kind of philosophy of like how do we look at wildness, and that is exactly what's happening after the break. So we're going to have a small 15-minute break, but before that I would like to invite everyone to give a warm round of applause to Navid. Please talk to him more. Go to the website again. And thanks a lot for being so generous.
Thank you.